We have one final talk in this session, which will be given by Iaroslav Melekhov, who will be talking about their solution that achieved the second place in the local feature challenge by using image stylization. Very exciting to listen to this. So Iaroslav, please take it away.
Yeah, thank you. Thank you so much, Torsten. Let me share my screen. No. It's why it doesn't work? No.
We see your screen. I think it's more of a question to going to full screen. Yep.
You see the, okay, I'm sorry. Yeah.
No problem.
Right. Hello, everyone. My name is Iaroslav Melekhov, and I'm a computer vision researcher at Aalto University. And I'm going to present our runner-up entry to the local feature matching challenge based on our technical report titled Image Stylization for Robust Features. And this work was carried out by during my internship at Niantic Labs last year. And I'm very thankful to all of my mentors and collaborators during this work: Gabriel, Brostow, Juho, Kannala, and Daniyar, Turmukhambetov. I'm very grateful for their support and guidance during the whole project. So in the next 10 minutes, I'll briefly talk about the visual localization, the problem of visual localization. We'll discuss the challenges the localization datasets exhibit and how we can use photorealistic image stylization techniques to overcome some of these challenges, and would it be possible to learn to train a local key point detector and descriptor to be more robust to different lighting or weather changes. I'll briefly present the results obtained by our approach on this challenge, and I'll conclude the talk by some summary and observations we did during working on this problem. So let's first look at the localization pipeline. I think it's very well known for the community and for the audience. So first we have a query image, and we retrieve top K database images, similar reference images, using some global image descriptors such as netflat or denseflat. So then key points are detected in each image independently, and corresponding descriptors are extracted. This can be done either with classical methods such as SIFT, or some learned descriptors, learned models such as Superpoint, D2Net, R2D2. So then the features are matched by nearest neighbor matcher, looking up the closest neighbor for each key point in the feature space. There is also like a filtering stage to remove some tentative correspondences produced by nearest neighbor matcher. And after that, we have like a list of 2D correspondences. Since some 3D scene representation is given, and based on the list of 2D correspondences, we can obtain a set of 2D 3D correspondences, and we can use this list to estimate camera pose using Coleman. So during this work, we are focusing mostly on this second part of the pipeline. So we would like to estimate to make our local key point detector and descriptor is more robust to different lighting conditions and very challenging conditions. So, and we are experimenting with R2D2 model. So, but the ideas presented in this work are applied to any other learned key point detectors and descriptors. So why it is important? I think almost all of the existing data sets for image-based localization are quite challenging, consisting of images taken during the different illumination or weather conditions, weather lighting conditions, and sometimes we can see like some direct light, which makes our work to localize query images much harder. So then the goal is to learn local key point detector and descriptor, which will be robust to different weather and lighting conditions. However, learning features that are invariant to illumination or weather changes is challenging, as suitable data is not easy to acquire. Ideally, the training data should consist of static scenes captured under various illumination or season changes. And one of the possibilities is to use structure from motion data sets. And those systems, structure from motion systems, can create 3D models from internet images that are captured at different times and weather conditions. However, and furthermore, using this training data allows us to improve the robustness of our local key point detector to appearance variations. However, building 3D models using this kind of images taken under extreme changes is much more difficult problem. So another direction is just using random images with some synthetic color augmentations. But we will touch this problem a bit later during this talk, and we will show that using just only synthetic color augmentations, color augmentation itself is not enough, is not sufficient. Or the third option, the third direction, is using webcam archives, where the stationary cameras around the world just broadcast and capture images for many, many years. So, and if we just touch this third direction, there are several options. So the first data set is the Amos data set. It's quite huge and constantly growing publicly available data set. Represents outdoor scenes captured by static cameras. We store images in all seasons and during the whole day. However, the data set has its own limitations, such as the fact that the scenes are not completely static and cameras have technical issues. For instance, they are out of focus and representing limiting dynamic range. Milan Pultar just tried to overcome some of the limitations of the original Amos dataset. So he just introduced a semi-automatic procedure to remove some bad images, some low-resolution images from the original Amos dataset, and removed moving objects and blurry images. So, and as a result, there is a data set representing 27 static scenes, 50 images per scene, captured by static camera exhibiting different weather and lighting conditions. However, the filtering processing proposed by Milan is not perfect. And as we can see from this example below, these two images representing different weather conditions, they are not so they do not represent static scene, since we have two objects like a van and crane in the right image, but we do not have those objects in the left image. So basically in this work we consider six different styles: cloudy weather, dusk, mist, night, rain, and snow. So we use the subset of Amos dataset produced by Pultar and manually sample 10 images for each style. So the sample images have been post-processed manually by removing watermarks and timestamps. So, and at the results here, we just demonstrate some of the examples. So we these images for each style we considered are illustrated here. So as I mentioned earlier, for each style we sampled 10 images with different appearance. For example, the night style has these style examples. So this allows us to generate multiple stylizations for the same image, meaning that single day image can be stylized using 10 different night images. So as it is represented here. To train our model, we used the phototourism dataset. In particular, from each training scene of the dataset, we randomly sample 300 images. And then we generate its 60 stylized versions, stylized copies. For image stylization, we use the method which is called Fast Photo Style by NVIDIA, and it preserves edges and objects after stylization, unlike other methods designed for artistic style transfer, such as GAMs. We train our networks using original and stylized image pairs. Crops are extracted from the original and stylized images using random homographies. So we do not use 3D geometry to find pixel correspondences between two views. So basically this method is trained on only synthetic transformations. And the image stylization and synthetic homography augmentation together allow us to learn features that are robust to appearance and viewpoint changes. And during training, we optimized the objective function, which was originally proposed by RStudio2 authors. And the network was trained for 70 epochs with warm-up and exponentially decaying learning rate. But still there is like a question, since we can easily get this color augmentation, and there are quite like a lot of libraries to experiment with and to apply color augmentation to images. So there is a question which might arise in our head. Is it like useful to use stylization and to generate these stylized images? So trying to answer this question, we just trained 3 models. So the architectures was the same, but the first model, it's the first row in this table, was trained on original phototourism dataset, trained on original images. The second model was trained on the same images, but with quite diverse synthetic color augmentations. And the third model was trained on stylized images. And as we can see from this table, the stylized images, so color augmentation can definitely help compared to the first model, but still it's not sufficient compared to the model trained on stylized images, especially for quite challenging cases as snow scene of Silda dataset. With this trained model, we entered long-term visual localization data challenge. So the challenge consists of 3 tracks covering different challenging data sets. And the goal of the challenge was to estimate 6-degree of freedom camera pose for each query image of the data set. So in contrast to the local feature track where the list of images to be matched was provided, for the first 2 tracks, we were free to use any global image descriptor to find closest database images for each query. So for the first 2 tracks, the results obtained by our model were not that great. It is important to mention that we, for evaluation, we didn't use this like additional information that images were like images representing like image sequences or were captured by a camera rig with multiple cameras with known transformation matrices. So we didn't apply this information, didn't use this information to predict query poses. So that's probably why the results obtained by our method were not comparable. But at least for Silda, again, for probably one of the challenging scenarios for this snow scene, the results are relatively good. They are not great, but it is quite. There is a gap in performance. And for the third track, for the local feature matching track, we could secure, our model could secure the second place. So and we just experimented with different setups of our model. So we just extracted different number of key points and using some outlier rejection techniques. So, and apparently the model which like produced 2000 key points with Adalam outlier rejection method could get these scores. Yeah, to summarize, so we investigate if image stylization can improve robustness of local features to illumination, weather, and season changes. So we used just single methods and could get some good results, competitive results compared to other strong baseline methods. So the color augmentations, even though it is quite useful strategy, but still not enough for very challenging data sets. We also experimented with super glue, but apparently we could not get quite good results. But we didn't fine tune super glue matcher on our features because we didn't have a lot of time. So and the technical report is available online, and we are also planning to release pre-trained models and also the data set. Yeah, thank you so much, and thank you, Torsten, and co-organizers of the workshop for this awesome opportunity to present our work. Yeah, thank you so much.
Thank you, Iaroslav, for this great talk. If there are questions from the audience, please use the Q&A box to post them. I have one question. Did you try playing around with like completely outlandish styles, like not trying to go for photorealism, but going for the thing that were initially used in style transfer, so transfer from images to from paintings to images?
Not really. So we just decided to use and to utilize just like real styles, and we just manually like choose like these 6 styles. It is also a question why just only these 6 and not others, because it's almost like an infinite number of like styles. But yeah, we just ended up with this set of styles and use it for this challenge. We also experimented with different models, not just only with R2D2, but it's like this work is not finished yet, and it would be quite interesting to investigate and to experiment.
I can only recommend trying something harder. So we did some experiments in other contexts, and even though we went for like painting to image, it actually seemed to help. There is a border where it just becomes too hard, but there is definitely some advantages that can be had there.
So when you could preserve the geometry, so the edges of objects, and it didn't. I mean, this stylization didn't affect this, or it wasn't very important for this problem, for your problem you consider.
Yeah, exactly. We have one question from the audience. Could we use some similar stylization trick to emulate a bunch of different cameras and slight changes in the scene geometry, not only changing the colors but warping some parts of the image?
Yeah, that's quite interesting point. Yeah, of course we didn't experiment with that, but potentially it might help. Yeah, but if we use like probably I didn't get like the like this point like fully understand the point, but if we use like synthetic chromographies and train our descriptors using synthetic chromographies, would it be almost the same, or probably not? Okay, yeah, that's quite interesting point. Yeah, I think I should think about that. Yeah.
Part of this might be covered if you go for styles that do some minor structural changes.
Okay. Yeah.
Are there any other questions from the audience or from the panelists? So if you're a panelist and you can unmute yourself and ask a question if you want. If not, then thank you very much again.
Yeah, thank you. Thank you so much. Thanks.
So this concludes the first part of this tutorial. We will be back in a few hours. So more precisely at 6 p.m. UTC+1, which is 7 p.m. Central European time. And I hope to see most of you or all of you later as well. Thank you very much for attending the tutorial and see you later. Bye-bye.